know if this is too much, but I was going to go right into, so this is straight out of my book. This is a rotational motion problem. And I wanted to cover in particular three things: how to do derivations, how to approach these graphing problems, and how to do an experiment problem. And then I'll also cover what is partial credit, like how do we go about partial credit? Because you got to play the partial credit game, right? And it's picky. It's picky, and oftentimes I find it inconsistent and unfair. So in general, I recommend you over answer, and don't be afraid to speak sentences with equations in the middle of it. It just works. And if you're not used to that sort of language, you might feel like that's, can I say, because of the equation F equals ma, if we hold mass the same and the acceleration goes up, the force must go up. You can speak like that. So just letting you guys know that, okay? So let's begin with this. I'm going to do a rotational motion problem. So I want everybody to stare at the figure and at part A and absorb it for a second before I attempt it, and I'll mute myself. Okay, so this derivation classic style of problem on the AP exam, the number one difficulty that I would say most people encounter is how to do a derivation. And I have a couple simple techniques that I think would be really helpful for this. And I also realize that, like, probably some of you are taught of the Giancoli textbook, etc. You might not get a lot of practice in a problem like this. And I see this with students all the time. They get an A in their class. And then if you haven't done problems like this, just because you get an A in physics doesn't mean you're good at the AP physics exam. You have to practice the free response. That's it. That's the only way to get to it. So, but the cool thing is, like any other test, there are patterns. And if you do it enough, you learn the patterns. So let's start here with part A. I'll do it off to the side here. Now, one of the number one things I recommend if you're stuck on a hard problem for a derivation, jot down relevant equations. So we have here, maybe I would say step one. Actually, no, this would be a better step one. What is going on here? You know, what does that mean? That means, what is the physical situation? What is the physical situation that's going on here? Well, you have a mass connected across a pulley, and that's going to pull down, right? The force of gravity is going to pull that thing down. And that is going to affect a tension through here, which is going to cause a tension through here, which is in the end going to rotate this, right? So there's a combination of things. There's a rotational thing going on here, and there's a force thing going on. And so some of your relevant equations are, well, as a background, and I'm going to write extra that you don't necessarily need, you know, F is equal to ma as a general thing, right? And maybe you should put it as the sum of forces. The sum of the forces is equal to mass times acceleration, or perhaps you write it as F net in either the y or x direction. Remember, this is a vector. It's direction specific. So, but what I see going on here, so you have an angular acceleration, and that's alpha, right? We're looking for an alpha here. That's our end goal. And when you are given a derivation, here's a super important thing to take note of. When they ask you to do a derivation, and they give you the variables, you are only allowed in your final equation to have those variables in it and nothing else. So your final answer, for instance, can have a v in it, can still have an I in it, even though I give you an I here. Any derivation, when they give you these explicit instructions, it must be in terms of the variables they list only. Now, one other important thing is, doesn't the gravitational force greater than the, yes, it is. The gravitational force is greater than the tension. We will get to that. We'll get to that in a second. It must be greater, right? Otherwise, the system would not accelerate, right? You have a force imbalance. But in general, so just let me first speak about derivations in general. Again, you have to use only these variables that they list, and some of these can cancel out. That is possible. So you don't have to use every variable, but you can only use the listed variables. Does that make sense? So super important take-home point for today. Just make sure you hold on to that. Use their variables. Some of them, you might not use all of them, but it can only be their variables and none other. Now, the thing that's occurring here is we're looking for an acceleration, right? An angular acceleration. That angular acceleration of this thing, this cylinder accelerating, can only happen by virtue of a torque, right? Torque is going to cause that thing to accelerate. Allie's in here. All right, so torque is going to cause this thing to accelerate. Hello, Allie, if you're there. Sorry, here, I'll go to Brady Bunch view. Hello, if you're there. All right, so torque is equal to I alpha, right? And by the way, when I say jot down relevant equations, you will have the equation sheet, right? And so you can literally hunt on these. You will use these equations here, right? You got force times distance. That's the way I put it anyway. They put it differently. And I don't know if they list I alpha here. Oh, that one they might not. Of course, you should know some of these equations even independent of the equation sheet. All right, in any event, back to this. You have two equations here. Torque is equal to I alpha, and torque is also equal to a force applied perpendicular, the perpendicular component of a force applied to an object, times the distance over which it acts. Right? Okay. Now, so our goal is to derive an equation, alpha. So, by the way, when it says derive an equation, your goal is to get the quantity wanted, which is alpha, by itself. So our goal is to get alpha by itself. Right? So we could be like, oh, well, we got alpha by itself. We're done here. But of course, and I'll just leave it as force times distance. I'm going to change my pen settings real quick because I don't like how my penmanship is showing up. So we're going to change this cursor. That looks better. Now I have a dot cursor. Alpha is equal to force times distance over I. We're getting there. We got I, but we need, it says nothing. We cannot have this I in here. We cannot have D in here. We cannot have F. So we need to derive things to get it in terms of these variables. Well, let's talk about some things here. So understand that what's going on here is this is what you would call an Atwood's machine, right? And by the way, I realize this is a very difficult derivation. I picked this one because I figured I could teach you the most at once with it. So bear with me. I'm going to show you my bad. This was for what I was doing earlier to get a picture ready for you guys. But here's the free body diagram for this. And I'm just pasting this here. So boom. Okay. So to the question that was posed in the chat, this would be the free body diagram that relates to our object. You got mg pulling the thing down. And you have F of t resisting acting upward, right? And mg down must be greater than ft up. Otherwise, the system would not accelerate. And that ft there is the same as this ft here. So the free body diagram for the mass, as I illustrate here, you have the net force, F net, and I'll write it out in addition to having it illustrated there. F net is equal to ma, and in terms of the mass, we're going to call downwards the positive direction. By the way, super important point, one of my students is in here, notice, probably knows I pointed this out prior. When you have masses connected across a pulley, which is the Atwood's machine, another take-home point, remember that your directions for the two systems must agree. So if downward is positive for this one, rightward must be positive for this one. We'll get to that in a second. That matters when you get to your second system. So I'm calling downward positive because it makes it easier for me because this is going to be positive too. So now, what's acting in the positive direction? mg. That's acting in the positive direction. What's acting against us? ft. And that's equal to, we're talking about this mass here, big MA. Any questions on this before I continue? Because even that's a bit hearty. Okay, so I'll just do a quick arrangement. mg minus ma is equal to ft. So far, so good. Now, let's go back to what I derived earlier, but I'm just going to use it in this form. Earlier, we had this equation. I alpha, torque, one torque equation, you could set equal to the other torque equation. Force times distance, right? Now, this equation, maybe it'll help if I give you guys some labels. And please let me know if I need to stop. Again, this is a difficult problem. I wrote it that way intentionally. This is for the box. This is the equation relevant to the box. And this is the equation relevant to the cylinder. Now, when you've done Atwood's machines in the past, you might be more used to, well, I make one equation for one mass, one equation for the other mass, and then I plug one into the other and solve, right? This is not quite the same. This is the trick. The AP Physics exam in particular is very good about creating a problem that is like, spans different chapters, right? A lot of us were used to, we have this section on forces, this section on energy, blah, blah, blah. But the AP exam is very good at making one problem that is combining everything at once. And you must get used to that. And I realize this is difficult because some of the ways most of us are taught physics is very compartmental. But you got to get used to being cross-compartment. So anyway, this force, the force which is causing the thing to rotate is the tension, as we said. So we can plug that in. I alpha is equal to mg minus ma. And that's times the distance, right? So let's plug in. I'm going to intersperse using my own handwriting versus dropping in figures. So let's drop this in. Now, a quick overhead view of this problem, of this cylinder, is this is an overhead view of the cylinder, right? What we're looking at here, that's a top-down view of this cylinder. Now, the tension is pulling the cylinder, right? And the distance at which that tension acts is the radius. So that means that this d, the distance, because again, torque is force times distance. And in here, that distance is r. So I could go ahead and plug in r in there. So the equation simplifies slightly into mg minus ma times r. So far, so good. So we're getting there. Now, let's go back to our intention. Our intention is to create an equation that has only these variables. So we're getting there. We got it in terms of m, big M. We'll see if we get to little m, r. We haven't got to little m yet, but we got r and a. But we have this problem with our current equation. I'll put it again down here. I alpha is equal to big mg minus big ma times r. Now, what is ma again? Yeah, good. Thank you for asking. Better question is, where did that come from, right? What is ma again? Well, I did Newton's second law. I applied it to the box here. Does that make sense, Luke? Let me know if it does or it doesn't, right? I plugged in, what is m for the box? Well, that m is this m. Yeah, please always ask, because I'm doing this correct, yeah. And it's, it's just important to recognize that M in this case is big M, or maybe they would call it M1, right? This is another common thing. They might label this big M, or they might call it like M1 or M2. And it's super common that you guys get used to. Typically, I find most students are plug and chug monsters, but when they have to do it in terms of variables, they get a little confuzzled. I mean, you can do, of course you can. I don't illustrate it with arrows because it's just an extra thing I don't need to point out. But yes, of course, it is a vector. And what's most important, Mehmet, or I don't know how to pronounce your name, Mehmet, I'm not sure, is that you independently, just like you would for projectile motions equations, understand that you have an x plane and a y plane whenever you do this. And sometimes you might run into a problem like that. You can apply F net in the y or x directions. So anyway, back to this. Our goal is we still have I in this. We must not have I in it because the derivation said we're only allowed to have big M, little m, r, and a, and physical constants. So, but as they would on the AP exam, you're not expected to memorize your moments of inertia. So we get I is equal to 1/2 little mr squared. And now we just make a simple substitution. 1/2 little m r squared times alpha is equal to, I'm just going to do, no, I'll leave it like this. Now the rest is just simple algebra, right? Look, I got r squared on the left, r on the right. Those guys go bye-bye, right? So I'm just left with r on the right. I will multiply by 2. I won't do too much at once. So we'll say m r alpha multiply by 2 to get rid of that is equal to 2 times the quantity mg minus big ma. I'll make some more space underneath. And then now finally, I have my derivation. Alpha is equal to 2 times mg minus ma over little mr. We have fulfilled every requirement of this derivation problem. We have gotten alpha by itself. Alpha is by itself. And our final answer only has the listed variables and nothing else. It's in terms of big M, little m, linear acceleration, and the radius. Any questions on this? Again, don't so much worry about the derivation itself. Notice the techniques I'm using. That's what's most important, what you can derive from me in this short time. It's identify what's going on here, jot down relevant equations, and then I could put as a third step, just like plug stuff in until it works. That's fair. And when I first do these derivations myself, this is how I typically do it. I just jot down stuff and I cram stuff together until I get the proper derivation. That's how a lot of this stuff is done. All right, so again, this is not on any AP exam. This is my own problem that I wrote to simulate something on the AP exam, all the way down to how they would do the diagram. So I want everybody, I will try to zoom out so we could see this all. Everybody absorb part B. You have like 30 more seconds. All right. So you're never restricted to answering it in the order they want. I might recommend, oh, another typical thing, huh? Another typical thing in an AP problem where you have an original situation, but then I would have what you would call a modifier to that original situation. The original situation was the rope is wrapped around the pulley and wrapped around the cylinder as well. And it's pulling it and it's accelerating the cylinder as the mass accelerates towards the ground. But there's an amendment to it. It's, well, at time t equals t1, now the rope unravels. So now the situation has changed. So do be used to this too, that subparts will build off of a previous part and even change the nature of the problem. So this means that the rope is connected here. It's going to be tugging on it, accelerating it, but then at one point that rope is released, and thus the cylinder will continue to spin of its own angular momentum, correct? So we need to illustrate this. Now, we have to illustrate, so what happens at T1? Well, as the rope is pulling it, right? Because again, torque is equal to I alpha, which is equal to force times distance. So as we did earlier with our derivation, well, this is constant, this is constant, this is constant, and therefore this must be constant too. That might be physically intuitive, but I also wanted to show that it can be equatively intuitive. I don't believe that's a word. So because these are all constant, that means alpha must be constant. So alpha is constant until T1. And at time T1, that rope is wrapped around the cylinder. It is spinning it, it is spinning it, it is spinning it. And then it detaches. And then a discontinuity occurs, right? The angular acceleration drops to 0. Don't fret about things like that. You might say, oh, that's not, it can't just, that's an infinite change in acceleration. This is impossible. But that's okay. This is ideal physics, not real physics. I have seen it on prior AP exams, by the way, where they would accept it. If someone's like really freaking out, like, wait a minute, maybe they're going to want me to show that it decelerates, that's fine. You can. But you can do this ideally. There is an angular acceleration, and then it drops to 0 abruptly. Now, again, I did this graph first, which helps me do the second one. Now, with the angular velocity, it begins at rest. So the angular velocity, because again, we got this rope attached around here, right? And it's going to pull this thing, accelerating it, accelerating, accelerating it. So constant acceleration means a constant velocity or constant change in velocity. And it's going to be increasing its velocity, increasing its velocity. And then once the rope detaches, velocity is constant. So that would look like this. Constantly increasing, and then bam. Then it maintains. Any questions? Feel free to type them or say them out loud. Cool either way. Negative. Okie dokie. I continue. Let's see, how many do we have in here? 13. Okay, that's pretty good. All right. So continuing. We go on to the second part. Okay, another very, very common, very AP style question. You make a modification to the system yet again, but now they want you to speak in, first give an answer and then justify that answer using a paragraph length response. So absorb this real quick. I will mute myself. Now, the bit I want you guys to focus on here is, again, not just the physics, but it is how to milk partial credit. What are they looking for? So I used to be a teaching assistant at a college. There are, like in one of the classes, I was a teaching assistant and there were 100 students and they took, an essay style question. Do you think that the people who are grading 100 exams are paying, unless you're taking an English class, which is different, but if you're taking a physics or an engineering class, when they're assigning partial credit, all they're looking for, did they do this, did they do this partial credit thing? Did they do this partial credit thing, right? All they're doing is they're literally scanning with their eyeballs and they're saying, did they do this, this, and this? Oh, okay, they did all those, 5 out of 5. Doesn't matter how beautiful or how articulate your answer is. You have to think like, what are the key points that they might ask me for? This, this, and this. So this one's a rather long response. So again, this is how to answer this. So first of all, the answer is, it is omega 2 would be less than half of omega 1. And here is how I will justify it in a paragraph length response. So this is the way you should speak. Refer to relevant laws and principles. So according to the law of conservation of angular momentum, let's change this sizing here so it fits better. Let's go down to like 18. No, that's going to still be too big. Okay. So according to the law of conservation of angular momentum, angular momentum must be conserved. Even that might be, again, when you're milking for partial credit, state a relevant physics principle, build with it. The initial angular momentum of the system is I cylinder times omega 1. And I'll just put it like that. Obviously, if you're handwriting it, it might look nicer. I'm not going to plop in an omega using the ASCII right now. Okay, so the initial, well, here, I'll just go like this. It's just so it's clear for you guys, is I omega 1. Okay, if a second cylinder, if the second cylinder added was simply a cylinder with the exact same rotational inertia. So, but by the way, what does that mean? Like, that means it's the same shape, right? Remember, rotational inertia is a consequence of not only a mass, but how the mass is distributed. So this guy here, it's stubbier. More of its mass is concentrated further out, thus it is harder to rotate. So if the second cylinder added was a simple cylinder with the exact same rotational inertia, then the total rotational inertia would be double, which means omega 2 would be half omega 1. So I speak with equations when I can, and then I expand upon those equations as I speak. All right, but here's the thing. However, the second cylinder has the same mass, but here we said twice the radius, has the same mass, but twice the radius. This would, and I'm just going to improvise from here, this would therefore increase the the contribution of angular momentum to the system by something more than just adding another of the same cylinder. Therefore, it must be less than half. Does that make sense? Again, I know that's a bit of a mouthful. Now, let me show you. I will copy and paste what they would have, how they would assign partial credit to this. Okay, here you go. So 1 point for selecting the correct answer. 1 point, either using, because you could have done this derivationally, but you could either use a conservation of momentum either logically, in a sentence, or mathematically. Some way demonstrating that the rotational inertia of the second cylinder is more than double the first, right? That's the point. If the R is greater than, if this new radius is greater than the original, then the rotational inertia must be more than the first one. And maybe more than double is incorrect, but it's more than the first one. Then you got to correctly relate the rotational inertia of the initial and final systems. And then maybe 1 point for speaking coherently. Any questions on this? We're going to move on to an easier problem after this, one that comes from the AP exam. Anything on the stylistic of what I've done here? Anything at all? I'll give like 30 seconds in the chat window while yeah, no problem. Did that connect? I know that was a lot. I'm so sorry that this was such a mean problem, but in my head, I'm like, how do if I have somebody for an hour, how can I hit like 1,000 bullet points so that something sticks? Because most of you know at least some of this, right? But then it's like, I didn't think about that. That's why this problem is so mean. All right, now let's go to something a little bit more, well, something straight up from the AP exam. So here's this one. This is from the 2019 exam, obviously. So take a look. And look at everything up to A parts I and II. Now, here is where I like using this problem, because I imagine you might want to over answer this, and I would too. Once it says, oh, determine an expression, which means derive an equation, right? You might want to just do the whole derivation all the way through, but that's not what they ask for. It's a little confusing in my opinion. They say, derive an expression for the spring constant in terms of, well, I'm sorry, we do that here, but your whole point is you're setting that up for what's the data you're going to plug into that. So what I said was this. Well, let's talk about our approaches here. First of all, we have spring constant equations, right? So anything that's got K in it, we got two choices. F is equal to Kx, or another equation that has K in it. The only other big one you really expected to know is that the spring energy is equal to 1/2 the spring constant K times the compression distance squared. Both of these are accessible here, but I would find one a little bit easier. So again, you could orient this experiment however you want. Our only goal is to how do we show that the spring constant of the spring, it has the same value even for different compression distances. So going back with this jotting down relevant equations, understand the physical situation. So if I took the spring-loaded launcher, this is how I did it. On the actual AP College board, they did it horizontally. I'm doing it vertically. Doesn't matter, either one works. I thought this was a little bit more intuitive. We take this ball and we compress it these different distances, A, B, and C, right? Well, if we compress the spring, at the point at which it's compressed, it's going to be entirely spring energy. I'll say ES. When it's all the way compressed, so let's say I compress it all the way down to C, it's purely spring energy. And then once I release the system, I let the spring go, shoots the ball up in the air, and then it hits this height, right? So we're going to have a transfer of spring energy into gravitational potential energy. So you could set spring energy, ES, is equal to EG. So that's 1/2 kx squared is equal to mgh, where h, of course, is the height above the initial rest height, right? The uncompressed height. So you have the distance it's compressed here, which is x, versus how high the thing goes in the air. That's the wrong pen. This is the right pen. That's h. Okay? So you could set those two equal. Now what I'm using is I'm using the equation to guide the words I'm eventually going to write. And so blah, 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 determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a school physics laboratory. So, well, you can have things like you can measure height with meter sticks, you can measure mass with a scale, et cetera, right? And you can measure this with a meter stick, or maybe more accurately, a millimeter stick or a centimeter ruler, whatever. So determine an expression for the spring constant in terms of that. So now we just do a quick rearrangement. K is equal to 2mgh upon x squared. I think I did that right. Yeah, okay, I don't see any problems with that. Let me check my own notes. Yeah, that works. Okay, so now check this out. Look, by the time I finish this, now I'm actually able to answer this too. So all they literally want is, they would say, conservation of energy. That's full credit for that one. And the next thing is showing the derivation. So just to show you the partial credit that they assign, let me rearrange this all so it's a little bit easier for you all to see. And I'm going to copy and paste this all in here because I don't want to waste your time with me typing it. So here's the answer to this problem. So let's look at their partial credit. Now, this is my rewriting of the actual college credit used by, or the partial credit as per the College Board. So, state a valid equation that relates to relevant physics. I use conservation of energy. You could use F is equal to kx. That's no problem. Creating an equation that can feasibly determine k. Well, that was just our derivation, right? If you started off here and you didn't arrive at a correct final equation, you earn 1 point. And then finally, deriving an equation that isolates k and is algebraically valid. And as I pointed out again, you may have also used Newton's second law to arrive at the equation, k is equal to ma over x. You could do this too. This is just fine. Multiple approaches are acceptable. And they will have in their solution guides that they're given, that the teachers are given to assign partial credit, they will have these multiple pathways. All right, any questions on that? Now, use that whole basis for your answer of part B. I'll mute myself briefly. So, again, I think I will just copy and paste the answer in the best interest of time. But this is nice. Armed with your equation, it helps guide. And if I haven't said this before, I already have, but let me say it again anyway. Use equations to guide your sentences. Speak with equations. So you could say, okay, look, I got to measure M, G is a known quantity, H is something I got to measure, and X is a known quantity. And here it is, right? So you'd be like, okay, well, the mass, just call that M, equipment, scale, etc. Height, H, and meter stick is fine. Or how about tape measure, whatever. Maybe that's more appropriate if it goes up too high in the air. They won't sweat you on details like that, of course. And then you have, how about compression distance? Compression D, symbol X in my case. And how about a ruler? Now, here's what I'm talking about with the copy and paste thing. Let's take a look at how they do partial credit here. So give me a moment. I'm just going to find my non-existent pointer. And let me go through my answer and what they would assign here. So long, brutal answer. If I have any other recommendation I could give on this, over answer. And don't over answer in terms of explanation, over answer in throw out this equation or throw out this principle of physics and then mention this equation, blah, blah, blah. So first, measure the mass. So again, this one is asking you to describe the experiment, right? So answer in a dry, matter-of-fact, but succinct way. First, measure the mass using an electronic scale. Then orient the launcher vertically and place the ball on top of the spring. Mark this as the rest length of the launcher. This, I think, was even probably unnecessary, but maybe important depending on how they grade it. Measure and record the distance between this rest length and positions A, B, and C with a millimeter ruler, and record these as different compression distances X. So notice how I answer it, and then look at the partial credit. 1 point, proper equipment. 1 point, the measuring all the quantities. Another point, plausible procedure. So this one is looking for a little bit more sense. Noticing that you have to put at least 2 different compression distances, because you're running an experiment. You never run an experiment with just one trial, right? You're trying to determine, is this on A, B, and C? Now, by the way, look at this last point, describing a procedure to reduce uncertainty. Because remember, let's go back to the original problem. Let's see. Oh, they don't say it here. Wait, do they? Oh, they don't, even though they don't explicitly state it. Look, this is, again, I am just restating what is on the actual College Board website. Even though they didn't state it, you need a procedure to reduce uncertainty, which means, and here's the quickest, simplest BS point hack you can possibly make. You say, repeat this for 3 trials and take an average. That is the simplest answer you can give for that. Describe a way you could reduce uncertainty. Okay, well, do the same thing for each distance 3 times and take an average. That's 1 point. Does that make sense? So I know this is simple and straightforward, but my point is, this is something that's so obvious you might forget to point it out and thus miss the point. Okay. Last parts. Oh, I'm sorry. Here's the continuation of it. My apologies. I didn't give you the full thing. They do say, take steps to reduce uncertainty. My apologies. Blah, blah, blah. Okay. Part C. Describe how the experimental data. So now this is a weird thing. You're commenting on something you've already done. And this kind of like circular nature where you feel like you're answering the same thing again in a different way, get used to it. That's very typical too. And so answer it again. You would say, all right, well, plug in the measured mass and gravity into for all positions into the equation. And again, I'll speak with words and equations juxtaposed into the equation K equals 2mg over x squared. Should be 2mgh over x squared. Then for each distance, plug in the compression distance and corresponding height, h. Solve for k at each position. If the k is approximately equal at each position, then the student, or you could say, then the hypothesis is true. Again, what I keep finding over and over as a theme is that this is not a hard problem. It's just, what do they want me to do? What sort of partial credit are they looking for, etc. And if there's another take-home point you could do today from this class, I would say get your hands on the old AP exams and look at, you can find them online. Of course, they're in my book as well, and I go through them in detail. But the College Board also provides the questions and the answers, and get used to the format. Write your own answer from scratch, do that, and then compare it to what the AP exam does, and then adjust your answer. Because if you don't have one of the points that they list there, you're not going to get the full credit, no matter how articulate you are. That's just not how these things are graded. So get used to the habit of modifying how you answer to fit their criteria. This is shopping for partial credit. You will definitely get used to this in college in your chemistry and physics courses where you have essay-based questions. You will get to learn your professor and how they grade it. Because again, if you go to a big enough class, 300 to 600, I would be one of the TAs grading your 300 problems. And I would be like, nope, they did this, this, and this. They didn't do this 4 out of 5. I don't care about the rest. Make sense? Okay, last one. I will pause. Okay, so you wind this thing up and they're saying, like, what's the relationship between launch speeds and velocity? Well, as I said prior, use an equation to justify, use an equation to do anything. Derive an equation. So the sort of energy that's occurring here is you're converting spring energy into kinetic energy, right? So you begin with 1/2 kx squared, and that's being converted into 1/2 mv squared. Your halves cancel out. We are trying to relate mass and velocity. You could solve for it in either direction. I will here, so kx squared is equal to mv squared. We could go, I could be like x is equal to the square root of mv squared over k. You could pull the v out if you want, doesn't matter for this. By the way, I've seen this. I don't believe that this, you don't have to take it to this. You know, you didn't have to be like, oh, square root of v comes out, just so you know. So now I got x in terms of v, or you could also solve v in terms of x. So, and that would be x is, if I simplify that, square root of k over m. Now, this is, again, another thing, another category, last big take-home point of the day. Learn your graphs. Learn how this sort of graph would look. So this is like a y is equal to the square root of 1 over x thing. Learn what that graph looks like. Learn what different types of graphs look like. And that has a very particular shape. And by the way, if you didn't know what that looks like, well, then plug in some sample values, right? You could plug in, like, let's say, like, man, I have no idea what that graph's supposed to look like. Fine, use sample values. 1, 2, 3, 4, 5, or you'll have your graphing calculator. You could do that too. But let's say you're in a panic, you don't even think about that. You plug that in and you would end up with an inverse relationship like this. Right, plug in the sample values, you would get this. If I plugged in 1, it'd be square root of 1 over 1, that's 1. If I plug in 2, that's a square root of 1/2, etc. And then you would get this relationship, this inverse exponential decay. Whew, that is 5 on the money. All right, quick questions, throw them at me. This is bonus time. Anything you want, any problem you ran into, something I could do quickly, whatever you want. Throw something at me. Or you could go and enjoy this fine, momentous day we're having. Any questions from anybody, though? You're welcome. You sure? Nothing? Any topic? Any topic at all? Again, quick free help. Something on top of your mind? I love to do this. You're welcome. Anything at all? A momentum question. All right. I'll dig something up and I'll throw it out there quickly. Let me try to find one directly from an old exam then. So let's see what I can pull off in 10 minutes. You're welcome. You're welcome, Ellie. See you. I don't know when I see you again. If it's this Thursday, make sure to email me, please.
Okay, thank you.
Yep, you're welcome. Okay, let me dig up, here, let me just bring up something directly from my book then. Let me change my pointer because it's easier to see. Nope, let's go default system scheme. All right. Oh, Luke's coming back. How do you say your name? Is it Eunice? Eunice? Eunice?
It's Eunice.
Eunice. All right, Eunice. Okay. So momentum. I'm trying to think where I'm going to pull this from. As opposed to going from a question, I'm going to go directly from my source material in my book. I think that's that's best for this time frame. So let's see what I find. Give me a second as I'm locating it, because I have to dig through my book. The 2020 version. Okay, here. I'll share with you what I got on the screen. So here you go. Okay. So I'm just going to scroll all the way down to momentum. Okay, some quick things. Obviously, the quantity momentum is equal to mass times velocity. This is straightforward. But other things, make sure that, momentum is a vector quantity, right? So momentum must be conserved in the x direction and the y direction independent of one another, right? Must be, because these are vectors. So, couple things to note. Know what is an elastic versus an inelastic versus a perfectly inelastic collision. A perfectly inelastic collision is best called a sticky collision, right? Or an explosion. Two objects come together and then they get stuck. And you must know, this is always a thing they will probably get you on in the multiple choice, that in an inelastic collision, momentum is conserved, but energy is not, right? And they say that's because energy is lost due to internal vibration of the system. Personally, I think this is just one of those cases where physics is only a model of reality. It is not equivalent to reality itself. It is tremendously good at describing reality, but sometimes it is not fit for a particular situation. In any event, so an interesting thing here, right? You got two objects that are heading towards one another in different directions, and then they collide. Now, because they met one another at an angle, they will respond by going in, they will both go in the y direction. So do recall again that what's happening, there should be an x here, by the way. Initial x, m1 v1 initial x, m2 v2 initial x is equal to m1 v final x plus m2 v final x. Makes sense, of course, right? But a quick hack you could do for the second part is, look, there was initially, these things were not moving in the y direction. Zero momentum in the y direction initially, which means zero in the y momentum finally. So I could set initial equal to 0, and that allows me to simplify, and I can plug these into one another. Well, not their velocities, because those are different, but maybe I could use these in a greater equation. Now, again, as I said, in an inelastic collision, momentum is conserved, but kinetic energy is not. And I like to call those sticky collisions. Two objects collide, and then they get stuck together. And you end up with this familiar situation where the two come together. And then there's impulse, which is covered very sparingly, I would say. It's something that does show up It's not what I would call a high yield topic. You know, it shows up maybe 1 out of every 4 free response tests. And not problems, but whole tests. And this is meant to represent it. This one we won't have time to get through, but anything quick I could say about this? I can point out for you. So this is in the final page. This is in my chapter on momentum, but there is I remember the 2019 exam. Here, I'll bring that up for you. AP tests. Let's find the 2019. All right, here we go. Yeah, this one. Look up this one. This one gets folks. This is a momentum problem, but it's tricky because they ask you to sketch the speed of the center of mass of the system. And the system, in this case, is both of the blocks. You have one block stationary, one block sliding. What does its center of mass translation look like for the two together? It's not something you might have come across. So good problem to look at. And again, greatest darn thing you guys could do in the world, go through old AP exams. Learn how to do them. Try to do them from scratch first. Never just read through what somebody else has done and be like, I get that. It's a totally different thing to get someone's solution versus coming up with it on your own. And definitely an intention behind my book is guiding students in that process. If you're trying to learn, like the AP exam gives you the answers, but if you're not used to figuring out how to come about this, that's the whole purpose of the book. It's how do I teach somebody to answer these? Anything else quickly? Say 2 more minutes. What you got? Arpita, Eunice, Lisa, anything? Are all of you at like Bronx Academy of Science or Stuyvesant? No, I haven't written one for AP Physics 2 yet. I may in 5 years or so, because I'm shifting more into other things. A good one though? Yeah, no problem. You're welcome. God, what for AP Physics 2? I don't know. I'll tell you the biggest problem I have with a lot of these review books, they come from like Kaplan, Princeton, etc., is most of them are like basically review books, right? It goes through all the topics, but it doesn't give you, some of them do give you free response questions. So again, just find the old tests. I have not written one for that, but find the old tests, find the old answers, but try to do that test first. When you get stuck, refer. Do not simply read through the answers and be like, I get it. Because when it comes time to do it on your own, especially when you're under stress, it's not so easy. You got to be used to writing this out. You got to be used to typing out or writing your response, etc. It just becomes, you know, what people inappropriately term muscle memory. It's not muscle memory, it's procedural memory. It's an unconscious memory process. So, alrighty. Take care, everybody. I hope everyone is safe. And enjoy the great show that is this day in American history. All right. Bye-bye, everybody.